Learning from demonstration, and more specifically, constraint learning and constrained inverse optimal control, have proven to be powerful tools for teaching robots to perform tasks. However, a core problem in these methods is the unidentifiability of the constraints. Oftentimes, there is an infinite set of possible constraints which can explain the demonstrations. If we entirely ignore the uncertainty when planning with the learned constraint, the system can act in an unsafe manner. On the other hand, trying to satisfy all possible constraints may be overly conservative and can lead to the planning problem becoming infeasible. In this work, we navigate this trade-off by proposing the following strategy. Our method takes locally optimal demonstrations as input and extracts a set of all constraint parameters which are consistent with the demonstrations. This informs our belief over possible constraints. We use this belief to plan a trajectory which is safe with some prescribed probability according to the constraint belief. We execute the trajectory and replan based on the sensed constraint data. This constitutes our policy. Let's take a closer look at these subcomponents. Denote f theta as the set of all constraint parameters theta which make the demonstrations locally optimal, that is, which make the demonstrations satisfy their KKT conditions. As f theta contains all theta which can possibly explain the demonstrations, it reflects our uncertainty in the constraints and thus is vital for constructing a belief over constraints b of theta. In section 4 of the paper, we describe how we can extract f theta from demonstrations. While it can be challenging to extract f theta for general constraint parameterizations, for certain useful parameterizations, f theta has a special geometric structure which makes it amenable to extraction by solving a sequence of mixed integer programs. Please see algorithm 1 in the paper for the specifics. We will use f theta to inform our constraint belief b of theta, which assigns probability mass based on some constraint prior p of theta defined over the theta belonging to f theta. We wish to design a closed-loop policy for planning to complete a task under the constraint uncertainty described by b of theta. This policy interleaves open-loop chance-constrained planning, execution, belief updates using the constraint data obtained in execution, and replanning using the updated belief. For open-loop planning, we use b of theta and plan a chance-constrained open-loop trajectory, which completes the task at hand, while ensuring that the trajectory is safe with at least some probability, where the probability is measured with respect to b of theta. Please see sections 5.1 and 5.2 for more specifics on open-loop planning. Our method can perform belief updates using various types of constraint measurements, including direct sensing, such as from a bump sensor in the case of obstacle constraints, range sensing, such as from LiDAR, or uncertain contact measurements, where collisions cannot be localized exactly on the robot volume. Please see section 5.3 and appendix D.4 for more details. To facilitate real-time execution, under certain assumptions detailed in section 5.4, we can avoid computing belief updates and open-loop trajectories online by pre-computing a policy tree, where the pre-computed contingency plans are rooted at possibly unsafe points in the plan, which under these assumptions can be known before execution by checking f theta. If these assumptions do not hold, we can always compute the belief updates and open-loop trajectories online, but this can be computationally intensive. Please see section 5.4 for more details. We are given a single demonstration of a quadrotor carrying a payload of an uncertain weight around uncertain obstacles. The uncertain obstacles are modeled as uncertain state constraints, while the uncertain weight is modeled as an uncertain constraint on the magnitude of the control input. As the demonstration does not activate all of the constraint boundaries, it induces both a set of guaranteed unsafe and possibly unsafe states in control inputs. In the center and right, we animate two viewing angles of the state component of the demonstration. On the left, we display the 2-norm of the control input component of the demonstrations. The black dots are the norms of the control inputs that are executed in the demonstrations. Here, the initial constraint uncertainty box is bounded because we assume that the initial feasible set of possible constraints is also bounded. We are tasked with steering the quadrotor from a new start to a new goal, Since it is not possible to satisfy all possible constraints, our planner plans this pink trajectory, which satisfies all possible state constraints at the cost of not satisfying some control constraints. Since this plan does not satisfy all possible constraints, we may violate a constraint in execution, so we compute contingency plans to switch to if we observe that the plan that we're following is unsafe. In this example, either plan 1 violates no constraints and we complete the task, or we violate a constraint and have to switch to a contingency plan. Contingency 1 may violate some possible state constraints, so we compute contingency plan 2 for if we end up violating a state constraint when executing contingency 1. We will need to compute a few more contingency plans in this fashion. We compare a policy to two baselines, the scenario approach, which samples constraints to satisfy, and an optimistic approach, which assumes possibly unsafe states are actually safe. On this sampled environment, our policy suffers fewer constraint violations than the baselines, since we optimize over the set of possible constraints to satisfy. A similar thing will happen for the second sampled environment. On this maze environment, we know the brown obstacles a priori. We are further given 5 demonstrations which imply the existence of 5 more obstacles, but the demonstrations themselves don't reveal much about the extent of these obstacles. Possibly unsafe states are shaded blue. We are given a new start and goal to steer between. In all subsequent videos, the bubble indicates the quadrator's constraint sensing radius. The trajectory that our planner computes for this new task implicitly trades off safety and performance. It realizes that the center passage is likely blocked by the uncertain obstacle, so it moves to the right and passes through the possibly unsafe region on the top right, since it reduces the cost by a lot, and it's unlikely that the uncertain obstacle extends all the way down to the brown obstacle. At this point, our sensing radius intersects with possibly unsafe space, so we can sense the true constraint. We discretize the set of possible constraint measurements and compute a contingency plan for each. Here's an example run of our policy. It ends up needing to switch to the contingency plan as the upper right passage is blocked for this environment. This baseline seeks to satisfy all possible constraints. As a result, it does not take online constraint measurements into account and deterministically returns a high cost trajectory. This optimistic baseline roughly only avoids guaranteed unsafe states. As a result, it greedily moves down the center passage, not realizing that it's likely blocked. This causes the executed trajectory to be higher cost. We are given 2 demonstrations which partially reveal the shelf constraint. We have 2 versions of each demonstration, one which is synthetically generated to be locally optimal, and one which is a recording of a human teleoperating the arm in a VR environment. We are given a new task, which is to move the arm from below to above the shelf for these new start and goal configurations. Our method performs similarly when initialized with human or synthetic demonstrations. We bump into an unmodeled obstacle below the shelf, which triggers an update of the constraint parameterization to 2 boxes. We replan, trading off cost and probability of collision, and this gets us to the goal. The optimistic approach, which only avoids edges if they are known to be unsafe, explores many edges and incurs a far higher cost. This variant of BTP, on the bottom right, needs to bump into the shelf several more times, since it is not provided with either the box prior on the world or the demonstrations which partially reveal the shelf. In summary, our approach seeks to plan with uncertain constraints that are learned from demonstrations. We extract a set of all possible constraints which are consistent with the demonstrations, and use this to inform a belief over constraints. We plan paths which are probabilistically safe under this belief, and execute in a receding horizon fashion, using constraint data gathered online to replan in case our initial path turns out to be unsafe. Finally, we demonstrate our approach on high-dimensional systems and high-dimensional uncertain constraints.